Hey, you made it back. Good deal. We are going to continue our discussion in AIT 1003 about pneumatics, and we've been talking, as you know, about pressures, temperatures, and volumes. We've got one more guy to talk about, and this guy's name is Mr. Joseph Lussac, and he told us that if we kept our volume the same, that our gas pressure and its temperature will have a direct relationship with each other. Now, you remember Charles said that if we kept our pressure the same, that our temperature and volume had a direct relationship. Mr. Lussac says that if we keep our volume the same, we'll be able to prove that there is a direct relationship between our temperature and our pressure. Okay. One little fun fact about this guy here. All right, he was not an alcoholic that I know of, but he did, however, come up with a way to determine an alcoholic drink's alcohol by volume. Okay, the formula there for that. He came up with that, which I think is kind of pretty cool. But also, I like to find applications, first of all, real simplistic ones are ones that you don't have to necessarily be involved in industry to understand. But the one that really proves this point is with the use of a bullet. Okay? Now, I got all the parts lined out here for you, okay? The casing holds the bullet in place, and you've got powder, and you have a primer that will ignite the powder, okay? It will burn the powder. And remember, Lussac said that a gas's pressure will increase when the temperature does, all right? So what happens with a bullet is we get our primer started that starts the burn of our powder, okay? Well, the burning of that powder increases our temperature, all right? And what's going to happen is our pressure is going to start building. And with the increased temperature, and this all happen just like that, you know that. But as our temperature increases, our pressure increases to a point. Now, our volume is staying the same. The volume is staying the same, but our pressure is increasing to the point where finally the casing can't hold the bullet anymore, and the bullet takes off down the barrel of the pistol or the rifle, whatever is going in. Okay, so there's a practical example of Mr. Lussac's law in order, or at work, I should say. And so another one is a pressure cooker. You know, our volume of our pressure cooker is not changing. However, our temperature is, and of course, our pressure is going up in proportion with the temperature as well. So there's that direct relationship. We're going to prove that a little bit more. Like I said, I like to use industrial examples. And again, this came in your book. It's pretty easy to understand, and the numbers are there for you in case you get off track or you need to try to figure something out. But we have a receiver tank on our compressor, okay, that's holding a certain volume of air. In this case, it's 10 cubic feet. But remember, Lussac says that the volume is going to remain the same. So for his example, we're not going to have to worry about the changing volume. However, we're going to start with a temperature of 75 degrees and 120 psi. Okay. So what we're going to do is we're going to go from 175 degrees up to 110, and it's going to tell us that our pressure is going to increase, okay? But we want to be able to prove that, okay, and show it how much it is and what the relationship is there. So again, we'll cover this one more time very quickly. Atmospheric pressure, 14.7 psi. Anything above zero on our gauge, you add those two together, and you wind up with absolute pressure. Okay, I don't need to go through this anymore. Same thing with Rankine scale and our temperature. 0 degrees Rankine is absolute zero when our molecules stop moving. And to get that, we simply just take the 460 degrees and add it to our ambient temperature. We wind up with Rankine temperature and Rankine scale. And to convert back to Fahrenheit, we just take the Rankine scale number, subtract 460, and here's our Fahrenheit number. Been over this a lot of times. Just want to keep driving it home for you. Okay. Now it's time for formulas. All right. We're dealing with pressures and temperatures this time. Okay. So our volume is going to stay the same, and the first thing we want to do is what? Get that thing linear. Okay. We're going to take our denominator and our fraction, move it over here to this side, and multiply it by whatever's on this side, and then you are left with that, and it looks a lot like that. Okay. So we're going to have T1 times P2. P1 times T2, and let's go ahead and put this into play, okay? I went ahead and put the formula up there so we could reference it at different times. So we have a starting temperature of 75 degrees, and the temperature is going to bump up to 110 degrees. and we have a starting pressure of 120 degrees, and we want to know what that temperature is going to be. Well, we know it's going to be a direct relationship, and we know it's going to go up because Mr. Lussac has told us that. So we want to just figure out exactly what it is, though, okay? So start dropping numbers in, okay? T1, 75 degrees, okay? And we have 120 PSI gauge and 110 degrees Fahrenheit, but we know that these numbers won't work. We've got to convert them, okay? So we're going to convert our 75 degrees Fahrenheit to absolute value, and that's going to be 75 plus 460 will give us 535. We are looking for P2, so it's going to stay there. We don't do anything with it, just kind of let it hang out for right now. All right, and we have 120 pounds per square inch gauge pressure, but we need absolute pressure. So we're going to add 14.7. That 120 becomes 134.7. We're going to multiply that by T2. T2 is 110 degrees, but we needed an absolute. We're going to add 460 to that, and we're going to wind up with 570. So this is our final, this is our formula here with all our variables in here up to this point, okay? And we are looking for P2. So we're going to multiply 134.7 by 570. It's going to give us 76,779. And that's equivalent to 535 times our P2, which is what we're looking for. And we said in the last video, in order to find out, we want to get P2 by itself. In order to do that, we have to divide whatever's hanging out with P2. On this side, we got to divide it by that. So 535 divided by 535, so these can cancel out and leave P2 all by its lonesome. All right, but if we're going to do it to one side, remember, we've got to do it to the other side as well. So we're going to divide our 76,779 that we got in our last step. We're going to divide that by 535, and that's going to give us our P2 of our pressure of 143.51 pounds per square inch absolute. But we're not quite finished because we want gauge pressure, and to do that, all we have to do is take that number and subtract 14.7, and we wind up with 128.81 pounds per square inch on our gauge. So what has happened is we started out with a temperature of 75 degrees and a pressure of 120 psi, okay, on our gauge. Then our temperature went up to 110 degrees and our pressure went up to 128.81. So you can see with temperature increasing, so does pressure, okay? So we have proven Mr. Lussacs Law, just like we've proven the others, and that's the impact it has on our system. That, folks, is our three main guys that we needed to talk about. One of them, remember, looks like Slash from Guns N' Roses. But the rest of them have brought us some very valuable information on how to determine how these impact the temperature changes, pressure changes, volume changes, how they all interact and relate with one another. Okay, and these have impacts on our pneumatic systems as to how our cylinders are going to perform, how our actuators will perform. Are we going to have enough volume in our air compressor? Okay, can it keep up with it? Can it create enough pressure? Can it keep up with the volume? So all of these things now you should be able to know, and you're going to need them as you move forward in the pneumatics part of this program. Okay, so, or the fluid power part of this program, I should say. So anyway, that's it for you. I'm going to shut this one down. And if you've got any questions about what we've covered through any of these lectures, please come see me. You can call me. Swing by the lab. I'm here on Tuesday nights from 6 to 10. But just swing by and see me, and we will work out whatever problems you got with these, and we'll go from there. Other than that, hey, thanks for watching, and I hope you've been taking notes, because Lord knows you're going to need them, okay? You're going to need them for that quiz, and you're going to need them for future classes too, so don't throw those notes away when the class is over, as badly as you probably want to. You're going to need them, okay? So anyway, there we have it, and thanks a lot for watching. I hope you've learned something.